All right. So the plan is to talk about group theory, in part because it's really close to my heart, and in part because I'm taking a really good class on it right now, with the goal of sort of combining the two traditional approaches. You often see, and I often saw when I got into group theory or was trying to learn it, half of the content I would see would introduce it in some format based on like axioms, and another sort of set of presentations would be symmetry based. These were the two ways that I saw this presented, and it sort of felt to me like if you learned it one way, it was really hard to think of it the other. And so I want to show that these are equivalent. That's basically the goal here today, is to show that an axiom-based creation of group theory and a symmetry-based idea of group theory are the same. So let's start with the axioms. So a group, here, let's write this out. A group G is a set equipped with a binary operation that we write multiplicatively. So denoted by multiplication, with the following axioms. So, well, let's start with axiom 0. Our group is closed under its operation. And I say 0 because we usually take this to be a property of the operation as opposed to a property of the group itself. But nonetheless, we require that, so for every A or B in the group, we have A times B is also in the group. And for ease of writing, we'll say we'll write AB to mean A times B. So this is like multiplication. You should sort of be familiar with this. It's not too crazy, but we almost always write the group action multiplicatively, and we almost always drop the multiplication sign.
All right, so A, B are elements in the group, right?
Oh, yes, exactly. Sorry, that's what this in symbol means here. It means that we've got two elements, A and B, in the group, and we can take their product, and we are guaranteed that that product is still in the group.
Got it.
And then we get into the actual axioms. There exists an identity element, written E, almost always, such that, well, it behaves like an identity element should. G times E should equal, E times G should equal G for all G in the group.
So you're saying like multiplication here, right? What are some, like, is it always multiplication? Like, what's the operation that can be used?
Yeah, so we'll get into that a little bit. But so frequently what we'll have is really, and sort of the point of today's lecture is that this is almost always actually some sort of function composition operation, or can be interpreted as such. But once I've outlined the axioms, we'll look at a couple of things that can be groups to evade your question for a little bit. Let's see. So multiplication is associative. This should be somewhat self-explanatory, but I'm going to write it out. So if we have elements A, B, and C, we have that AB times C equals A, B times C equals ABC for A, B, C in the group. And then finally, G contains inverses. For every G in the group, there exists a unique element, G inverse, such that G times G inverse, and I'm gonna just copy this so it's easier to type, equals G inverse times G equals the identity. So every element G has another element in the group that sends it back to the identity under multiplication. So if we were thinking about an operation of addition, this would mean that if a number is in the group, the negative of that number is in the group, and you can add them up and you'll get 0. If you're thinking about multiplication under the real numbers, this means that we have reciprocals, things like that.
But they have to be different, right? So you can't. Can the inverse be the same as like the original element? So for example,
it absolutely can.
Yeah.
Okay, yeah. So 0 can be its own inverse.
Exactly, and in fact, it has to be its own inverse. And
right.
in fact, it has. Yeah, there cannot exist any non-identity element that sends the identity to the identity, right? And so,
yeah, that makes sense.
Yeah, and notice that I said that this G inverse is unique. We don't have to demand this. This doesn't have to be an axiom. It's provable from these axioms. But because it's provable from these axioms and like pretty easily provable from these axioms, oftentimes we'll just demand it to save everybody the effort of proving it. This too. The identity is also unique. There. All right. So let's evade the question of what sort of things behave nicely as groups for a little bit longer, and talk about symmetries. So I've put these. No, let's talk about one example of groups first. So I was going to say I've put these out here, and I don't want you to worry about them too much because we'll talk about them more. But let's talk about some simple examples. We have. See, is this going to work? No. We need. Integers mod m. Integers under addition modulo m. So these are called the cyclic groups of order m for reasons that we'll talk about. But basically, we can, if we perform the operation of addition modulo m, we have, we have these axioms satisfied. It shouldn't be too shocking that 0 plays the role of the identity. Our operation is addition, and everything has a unique inverse. The equivalence class of, and let's say every G. Is that going to display weirdly? Let's do A. Every element A, whatever, that's fine, has a unique inverse, which is the equivalence class of negative A. So we tend to think of the integers mod m as being between 0 and m. So when you take sort of the negative of an integer, mod m, we tend to think of, okay, let's wrap back around and stay within the range 0 to m. but you find the correct equivalence class by taking sort of negative A. So maybe we have, let's have the integers mod 3. We have this set that looks like 0, 1, 2, where 0 is the identity, 1 is the 1. Let's see, 1 and 2 are inverses, because when you add 1 to 2, you get 3. Mod 3, we go back to 0. Note that 1 plus 1 equals 2, and 2 plus 2 equals 4 equals 1 mod 3. So 1 and 2 invert each other, but not themselves. Make sense? I know that's sort of, hopefully we're comfortable with modular arithmetic like this. This should be okay.
Yep, makes sense.
All right, now let's talk about symmetry. So a symmetry is, what is a symmetry? It's sort of a relabeling of some group of things, some set of things. I should be careful of my language. It's a relabeling of some set of things that preserve some structure that we impose. So is a relabeling of a set that preserves some imposed structure. So this is where I want to be able to draw, because maybe we have a square, something like this. All right, we'll connect the sides, and we'll label the vertices. And a symmetry of this square would be something that preserves all of these sides. So we're going to have this list of vertices. 1, 2, 3, 4. And we're going to permute them in such a way that if we fill back in, if we relabel this vertex something, and we relabel this vertex something, et cetera, there's still an edge between 1 and 2, and there's still an edge between 2 and 4, and there's still an edge between 3 and 4, and there's still an edge between 1 and 3. That's a symmetry, where it's the symmetry of this square looks like some permutation of the vertices that maintains the edges. The structure that we've imposed on this is that the edges stay the same. So one thing we might do, one possible symmetry looks like 90-degree rotation, right? So let's get this drawn, and it's gonna look the same, of course, because we're requiring that as a symmetry. But now I've labeled this in a sort of a poor way. Let me 1, 2, 3, 4, because now when we do our 90-degree rotation, well, 1 is over here. Come on. Is that going to work?
Think about this in terms of like graphs, right?
Yeah.
Are you familiar with like graph isomorphism?
Yep, and that's an important word here.
Okay. So basically, it is a way to describe this saying like you have like an input graph, which is on the left here, and an output on the right. Like you map you map one thing to another, like one node to another, one number to another.
Exactly right, but it's a mapping of nodes that preserves the edges. So if we describe the edges in terms of, this edge right here rather than being between 1 and 2, we say this is the edge between the first vertex and the second vertex. And so if we now have 4, 1, 2, 3, which is this permutation here, this edge is now between the first and the second object, which are no longer vertices 1 and 2, but it's still an edge that existed in the original graph. So we've maintained sort of the set of edges, even though we've moved the vertices around. But yeah, a graph isomorphism is an important idea because an isomorphism is not just a bijection. We tend to think of it as such, but so a bijection is a one-to-one remapping of the vertices. But an isomorphism is more than that because it's a bijection that preserves some sort of structure. A bijection on its own may not respect these edges. So we demand that these edges are preserved, and so there are fewer isomorphisms than there are bijections.
So actually, I guess a follow-up question is, what do the edges represent in terms of like groups?
They are just some structure. So we're getting there. That's actually an excellent question. We're getting there. So this is this 90-degree rotation. Yeah, so there is some sort of meaning there, but hold on a second. Can I do this? Good. Okay, so let's look at just something that is a bijection but is not an isomorphism. Or yeah, so isomorphism is an appropriate word here, but what I really mean is a symmetry. So suppose we go down here and we are going to swap vertices 2 and 1. We're going to leave 3 and 4 alone. Now, if we draw back in the edges that we want, so we want an edge between 1 and 2, we've got that. We want an edge between 3 and 4, we've got that. But we want an edge between 2 and 3, which looks like this. And we want an edge between 1 and 4, which looks like this. And so you see that we've twisted our square. We've flipped the top 2 vertices. You imagine the square might be made out of string, with the vertices being like beads or something. We've made a loop in our string. So this is not a symmetry. Not symmetry.
So sorry.
Yeah, sure.
You care more, like you also care about the shape, not just the connections that the shape has, right?
Exactly. You might think of symmetries as ways that we can move the shape to allow it to take the same space.
I see. Okay.
That's another valid, but that notion of space is some structure that we've imposed on this set. Yeah. So really fundamentally, we are interested in the ways that we can permute the vertices without changing the structure of the square in some meaningful way. Is that sort of fair?
Yeah, that makes sense.
Cool. Let's see. Got more space down here. Good. Okay. So the other lesson to be had here is that we have to choose what we're actually trying to preserve. So like this is a set of 4 vertices, right? This is the set of vertices 1, 2, 3, 4. There are 4 factorial ways to permute these vertices. There are not 4 factorial symmetries of a square, right? So we need to choose something to something to preserve and then preserve it, and that actually restricts how many remappings we can do that respect what we've chosen to preserve. Right. So yeah, let's talk about this a little bit more, actually. What symmetries do we have in the square? If I draw another square down here, and now I'm not going to be well, I'm still going to label the vertices. 1, 2, 3, 4. What are some symmetries? Type, is that gonna what?
You have rotational symmetry.
Good. Rotations. By what? What could we, in what ways could we rotate? Because if I rotate 1 degree, that's not a symmetry, right? We've disrupted space.
Right. So 90 degrees, right?
By 90 degrees.
180. Or 180 I guess that could,
yeah. Any multiple of 90, right?
Yeah.
Exactly. And I am happy about abstracting that so quickly. Any multiple of 90 degrees. Because if we imagine a 90-degree rotation as a group element, and we multiply it by itself a bunch of times, every time by multiply I mean compose, we do it again. We do a 90-degree rotation repeatedly. There will be some composition of those rotations that we have to add to our group in order to maintain closure. So you think about when you put a 90-degree rotation in there, you also have to put all multiples of 90-degree rotation in there. But we'll get to talking about that a little bit more. What else do we have? It's less obvious what else we have, but there's something more. You can reflect.
All right.
Why can you reflect?
Because
a silly question, but
like the structure, as you said, would be it would still be there if you reflect across the diagonal axes, and also if you reflect it from like the x and y axis.
Perfect. I agree completely. So we have this axis of reflection, this axis of reflection, and we have the diagonals. That's very astute and not really obvious, not to me anyway. So these are the reflections we can do. So if we go back here, reflections. About coordinate axes, diagonals of the square. How many symmetries do we have? How many rotations?
You got 3 or 4. I'm gonna say.
This is 3. An excellent question. Why do you say 3?
Because if you do 4, right, that's just a full 360 degree, which gets you to the same spot, which is sort of like the identity.
Exactly, but what is the identity? I mean, okay,
Ooh.
Sure. Let's say, hold on. 3 rotations, right? 3 distinct rotations. How many reflections?
1, 2, 3, 4.
4 reflections. And then maybe we circumvent the idea of putting the identity anywhere by just saying we have one identity, which is do nothing. Just leave it be, right?
I like that suggestion.
Typically, we would consider the identity a rotation exactly because it is sort of the 4th power of the 90-degree rotation. But it doesn't matter. You can say that we have 3 rotations, 4 reflections, and an identity if you want. But you're right, you have to think of the identity. Yeah, I mean, and you have to think of the identity because the identity is a valid symmetry. So, what do we want to take away from this? What we want to take away from this is that we've just described a group. Why have we described a group? Well, what are the objects of the group? The objects are symmetries of the square, right? Hold on. Let's see. What group have we described? So objects, symmetries of the square. What's our operation? This is a little bit harder.
Rotation and reflection.
Or just like movement. I don't know.
Yeah.
So this is the tricky thing to reason about. What you both just described are actually these objects.
Oh, wait, yeah, you're right. Okay, yeah.
Right? So our operation, I've alluded to this, but I'll say it. Composition.
Oh, yeah, so like rotating once and rotating once again results in a rotation that's in the original group.
Exactly.
So,
closure. Of course, if two actions are symmetries of a square, they each preserve the structure. So applying them together still preserves the structure, right? If we have two rotations that are both symmetries of the square, obviously doing one and then the other, well, after we do the first one, the square takes up the same amount of space, and then we do the second one, and the second one is going to preserve the space it takes up. So of course the composition has to overall preserve the structure that we're looking for.
Makes sense. Yeah.
So that's our closure. Identity, yes, of course. Yep, taken care of. Associativity, let's come back to that one actually. And then inverses, obviously, because, well, if you reflect, what's the inverse of a reflection?
Reflection.
Yes, it's just doing the same reflection again. This goes back to your question, by the way, of can things be their own inverses? Yes, you can have things that non-identity elements, which when you apply them twice, you get back to the identity. And reflections are an example of that. Of course, rotations have to have inverses because you could just rotate the opposite direction. And it turns out that rotating 90 degrees clockwise, maybe I should draw this, rotating 90 degrees clockwise is the same as rotating the other direction 270 degrees. And you should verify that if you don't believe me, but you should also believe me. Because in both cases, if you follow that by rotation this direction clockwise by 270 degrees, in both cases, this is the identity.
Bold claims backed up.
Yeah, it should not be all that difficult to believe. Like maybe slightly harder to verify, but you should believe that every symmetry has an inverse. That's also a symmetry. If I do some action that preserves structure, then you're sort of starting in a state with the structure preserved, and you're ending in a state with the structure preserved. So if you play that backwards, you're still preserving structure, so you still have a symmetry. So why did I say associativity? Why am I coming back to associativity? Because this is either really glaringly obvious, or you right now don't believe me. Those are sort of the two ways that this could go. Why are group elements associative here? Because they're functions. The answer is because they're functions. We're doing some action to the square, and function composition is associative. So our objects are functions, they're actions on the square, and our operation is composition. So you should be comfortable with the fact that it's associative. Now, the problem with that, of course, is that what does it really mean for these symmetries to be associative? Well, it's a little bit harder to say.
Is it like applying the operations in a different order?
We have to be really careful. That's actually, thank you for bringing that up. But no, if we change the order, that's a question of commutativity. And groups do not have to be commutative. In fact, this is good. Commutativity only for what we call abelian groups. And this is named after this mathematician, Abel, who was sort of a founder of the field of group theory. And this literally just means a commutative group. So we don't actually require commutativity. So we do need to care about the order in which we apply operations. And if you think about that, like if you apply a reflection and then you rotate, that should be different than first rotating and then applying a reflection. Those should be different things. And they are. But associativity means that if I take, two rotations, apply them like one after another, and then apply a reflection, it doesn't matter if I were to first take, like if I were going to draw a square over here, if I were to draw a square over here, I was going to say, okay, what happens if I rotate by 90 degrees and then I reflect about, say, this axis, right? This gives me something. This is some symmetry. If I then take this and add another 90-degree rotation, that gives something. This should be the same as if I have to be super, super careful here. This should be this, well, okay, I should not have chosen. This will be 90 degrees and this will be 180 degrees so that there's a difference, right? This is basically, this is of the form A, B times this is C, right? This should be the same as if we do A and B times C. So if I go, I look at what it means to reflect about this axis and then rotate by 180 degrees. I apply that total operation, and then I do that after I apply 90-degree rotation. It's sort of subtle in exactly what way we're even doing anything different, but that's because we're so comfortable with the idea of things being associative. And this, we would just write A, B, C, because the order doesn't matter. Or because it's associative. Order matters, but the order in which we evaluate this doesn't matter.
The sequence matters, but like the
parentheses don't matter. Yeah.
Yeah, the parentheses. All right.
I could do this. Yeah. But the sequence does matter, exactly. Okay. So, but really you should just be like, okay, our objects are functions. They're actions on the square. And so their composition should be associative because function composition is. Okay. So what do we conclude? I mean, what's the point? The point is symmetries are groups. So if we want to come back over here and say, in fact, the collection of symmetries of some object preserving some structure forms a group. And we were talking about the square, but we didn't have to be talking about the square. I mean, nothing we said about the square is going to be different for, you know, a triangle or for, I don't know, even a trapezoid. I mean, the trapezoid will have fewer symmetries because rotation doesn't work. But if we take the collection of all the symmetries, it still checks off all these boxes about axioms that we looked at. So we sort of have one direction. We say, in general, the collection of symmetries of some object obeys, and let me really put this in bold for you, obeys the group axioms. That's not bold, that's whatever, italics is fine. There we go. So I really want to emphasize, the collection of symmetries of some object will obey the group axioms. Is the converse true? This is sort of, should be your immediate reaction. Is the converse true? If I have something that obeys the group axioms, is that the set of symmetries of some object with the operation of composition? And, well, it wouldn't be much of an interesting lecture if the answer was no. So, yes, but what object? So, in particular, if I have, let's get this out of the way, right? If I have a group G, and I want to know what object is G the symmetries of? Well, we have this quite remarkable theorem called Cayley's theorem. That, well, yeah, Cayley's theorem answers this question affirmatively, and there's this notion of a Cayley graph, which allows us to construct the thing which a group is the symmetries of. Construct its Cayley graph. So we'll say that G is some collection of objects. We're not even going to bother with this. I'm going to I'll specify what exactly we're doing. So we're going to say introducing the Cayley graph. So for a group G, we draw a vertex for every element G in the group, and between each vertex we draw an arrow. We'll say we draw an arrow from G to GF of a particular color, say CF. Yeah, well, this is a complete sentence. Why is this a complete sentence? because between each pair of vertices G and F. So we have some group element G, and we have some group, G and GF. So we have some group element G and some group element F. And from G, we draw an arrow to the thing that we get when we apply S to G. So we have G, hold on. I draw, thank you. We have G, F are elements of the group G. So G, F is also in G, right? Their product has to be in G. So we would have this thing here, this is G, this is F, this is GF, and of, say, this color, this. And then G might, then there might be some node, well, let's say over here, and this is G with two applications of F. And it's the same color because it comes from here by applying F. This is, we've applied F there. And then, but maybe over here, there's some other node, G prime. G, come on, work with me. G prime. And maybe it goes to GF squared, but it goes by some element, you know, S prime. So in other words, G prime S prime equals G times S squared. But the colors in the arrows represent what group elements we're sort of using to get from one to the other.
And you can have multiple like types of of these symmetries, right?
Exactly. So maybe G is a rotation and S is a rotation, but G prime is a reflection and S prime is a reflection.
Yeah. Okay.
Then ultimately the composition of some rotations will be some rotation, but the composition of some reflections will also be a rotation. So maybe we go from G to GF, or we go from G to GF squared by, this is sort of 3 rotations altogether, but G prime is a reflection and S prime is a reflection. So it goes to this rotation, but by a different route.
All right. So does that sort of imply that you have to be able to get to any point or like any state by using like any class of operations? So like you have to be able to get somewhere by using reflections or by using rotations.
So the thing is, we don't really sort of distinguish between reflections and rotations symbolically. So there's no particular reason to think of that, but it is true. If I want to get from G to G prime, I can do that by multiplying on the right by, well, by what? By G inverse G prime. And you can check that G times G inverse G prime is in fact G prime. And we've demanded that the group has inverses. And of course, G prime is some element of G because it's what we're trying to get to. So yes, there is actually a connection between every single node. at least one connection because we've just constructed that connection. But the color of the arrow reflects which element of the group gets us between these two nodes. And so maybe here it would actually be useful to draw a Cayley graph. So we're going to say, we're going to do this. It doesn't want to let me draw or let me write. Okay, that's weird. Well, let G be some set, an identity, and then some objects A, B, and C. Where A squared equals B squared equals C squared equals the identity, and AB equals C, AC equals B, BC equals A. So we've got some group where everything inverts itself, and if you multiply two non-identity elements, you get the other non-identity element. Okay, is this fair? Is this, I mean,
yeah,
this is not necessarily obvious how this is a symmetry, but it is.
Okay.
But, and you don't have to worry about what these symmetries are. The Klein for group K4. So we've defined some set and some operation on that set. All right. So let's draw the Cayley graph. So in particular, maybe we want to start by drawing the identity here. And then over here, we're going to draw A. And over here, we're going to draw B. And over here, we're going to draw C. And so, of course, the identity goes to A by A. But A goes back to the identity by A because we've demanded that A squared equals 1, or A squared equals the identity, I mean, right there, right? So A and the identity go back and forth by A. Likewise, B and the identity go back and forth by B. And that doesn't look amazing, but that's fine. C and the identity go back and forth by C, right? And then, of course, if we multiply B and A together, this should give us C. And if we multiply C and A together, that's also this. And A times B gives us C. C times B gives us A. And then finally, this. So this is the Cayley graph, and this reflects the way that we've defined multiplication here. Right?
Yep, makes sense.
This should be like this is a speak now or forever hold your peace sort of thing, because I know that it's sort of weird and abstract, but
yeah, no, that makes sense.
Hopefully it's acceptable.
Yeah, the only hesitation I get is from conceptualizing these nodes to operations because they're equivalent.
Yeah.
But like, it does make sense.
Right.
This graph.
So my point here today is to say that, like, you don't have to sit here and think of these nodes as actions. You could say, you know, A is some object and B is some object and C is some object. You could even think of them as standing in for some numbers. It's just that they will always be the symmetries of something because they're in a group, but you don't have to think of them that way, and certainly not yet. So in fact, what we're going to do is we are going to, right? Okay, perfect. What happens if we, I wish I could bold, but I'm going to do this, translate the Cayley graph by some element A, by some element, call it, or like let's pick A. So when I say translate the Cayley graph, that is, let's multiply every node by A on the left. So this is sort of important. Okay, good. So let's do that. Well, all we're going to do is we're going to leave every node in place, just for the sake of clarity. We're going to leave every node in place, and all we're going to do is multiply the nodes by A, and then redraw our arrows. So the identity, obviously, when we multiply it by A, we just get A. A, when we multiply it by the or when we multiply it by A, we get the identity, because we sort of stipulated that in our operation. B, when we multiply by A on the left, so what we're doing is we're putting an A here. That's an A, I promise. We're putting an A there. So A times B, we said was C. And C, when we multiply by A here, gives us B, right? This is what this is our multiplication that we stipulated here.
Yep, makes sense.
And now we look at this. We say, okay, A goes to the identity and back by A. And notice that I'm using blue to indicate A. And likewise, B and C go back and forth between each other by A, right? This blue means A. And identity and C go back and forth. Hold on. By C. And likewise, A and B go back and forth by C. Again, we're just applying the multiplication rules that we guaranteed here, or that we stipulated for the group. And then finally, of course, when we multiply the identity by B, we get B. We multiply by B by B, we get the identity. And A and C go back and forth by B. So that's curious. We have the same graph again.
Oh, damn! I just noticed that.
So in fact, if our graph, if we're going to graph the elements of G and stipulate that, if we create the Cayley graph of G and stipulate that the structure that we want to maintain is the directions and colors of all the edges, it turns out that the group elements are symmetries of this graph. If we draw the Cayley graph of G, yeah, so let's see, let me say that again. And we stipulate, and we demand that directions and colors of arrows are maintained, then the elements of G are the symmetries of this Cayley graph. Okay, fair?
Yeah, quick question.
Sure.
Is this the case if A, like in this case, A is its own inverse?
Right.
Because what if it's not its own inverse, right? What if, does that result in a different Cayley graph?
So let me prove to you that a Cayley graph always has symmetries given by the group elements. Proof. Let me grab my notes for this. So suppose we are looking at a vertex G going to GF by F. This arrow has a particular color, call it CF, right? We don't care what the color is, but it's associated with the element F. So that's like talking about, this arrow, right? That's what we're talking about. We're going to look at some node G, and we're going to look at where it goes. Now, translate the graph by H. So we're going to multiply everything in the graph by H on the left. Every node we multiply by H, and we look at where things go. So we have something that looks like this. We've got G, G, F. Hold on. They go to each other by F, of course. And note that we're not stipulating that this arrow goes back and forth. Like it just happened with the simple group that we constructed, that this always like works like this. But we're not demanding that. This is totally general. We don't know what group we're working with here. We just know that G goes to GF by F, of course. Now we're going to translate this to some HG by H. And then, of course, hold on. Of course, we know that HG multiplied on the right by F, this is HG times F, right? Because we've taken this node HG and we've applied S to it. So all we want is to say, does this arrow happen by H? Is that the translation? Well, of course it is, because in a group we stipulate that HGS equals HGS. This is exactly associativity, right?
Oh, clever.
Which means that this node goes here by H, just like this node goes here by H. And so this relationship this relationship by F is maintained. Now HG goes to, HG goes to HGS by in an arrow of color CF, of course, but HGS equals HGS. So this is exactly the translation of GF by H. Thus, our arrow is maintained. But this holds for arbitrary G, S, H in the group. So H is a symmetry of this graph. This is really the fundamental question here. I want to emphasize this. And in fact, I kind of want to sort of move stuff. Let me get this like over here. And then right. So how do we feel about this? Basically, the question is whether, yeah. How do we feel about this? I think this is amazing. I think that, showing that if two nodes have this blue arrow between them, then their translations have this arrow between them because the group is associative.
Yeah, makes sense. That is pretty cool.
And of course, because our group has inverses, there's some element that's going to be sent to the identity, right? Wherever H inverse is on this Cayley graph, when we multiply it on the left by H, we get the identity. So our new graph translated is, of course, going to have the identity. In summary, G, any group G, which follows the axioms of a group, is a collection of symmetries of some graph. In particular, it's Cayley graph. Notice that G need not be all the symmetries of particular graph. So in particular, what if we drew the Cayley graph like we did here, and then we've just added, some node over here, and some node over here, and some node over here. Well, then, we don't have to even label these nodes because we can permute just these nodes and leave everything else intact. And that's asymmetry of this graph. But it obviously, there are three ways to permute these nodes, or yeah, something like that. There's some number of ways to permute just these outer black nodes that leave the whole rest of the graph intact. So we have some symmetries of this new graph that are not, or that are all described by the identity element of G. So obviously G does not contain an element corresponding to every permutation of this graph. And in fact, it need not contain an element corresponding to every permutation of its Cayley graph either. But it contains some subset of the symmetries of its Cayley graph. And it contains every group is some subset of the symmetries of some graph. Preserving some structure. Thus, we have associated sort of groups and symmetries. Yeah, it's sort of an inextricable association between groups and symmetries. Everything that follows the group axiom is the symmetries of something, and the symmetries of any object you create form a group. So it's not that this is one way to look at it, and this is another way to look at it, but in fact, they are totally inseparable concepts. And lastly, what I wanted to do is just look at some interesting examples of groups. So we've looked at examples of groups. We looked briefly at Z3, the integers mod 3 under addition. What exactly are we going to do? Let's look at Z4, which is the same but under addition mod 4. And I don't want to have to type this over and over again, so let's just do this. Let's see. So of course Z4 is this set, right? We have 0, 1, 2, 3. That should be hopefully non-controversial. Of course, 0 is our identity. But let's look at what happens if we just take 1. Let's do this here. Let's just take, so we have C4, 0, 1, 2, 3. So let's take some element. Let's pick 1. And let's just keep applying it to itself. So this is in our multiplicative notation, we're taking powers of this element, but really we're working with addition. So we're just multiplying this element. So we have, of course, 1, and then plus 1 is 2, plus 1 is 3, plus 1 is 4. Hopefully I haven't said anything shocking there, right? That's sort of course. So why am I talking to you about it? Why do you care? We say that Z4 is generated by, in fact, this deserves caps, generated by the element 1. Because every element in Z4 is some application of 1 to itself over and over, some number of times. Does 2 generate Z4? How about 3? How about 0 even? You guys tell me, which of these elements generates Z4?
Can 3 do it?
I think so. Let's find out.
Yeah.
3 plus 3 is 6, which mod 4 is 2. Plus 3 is 5, mod 4 is 1. And so we've got 3, we've got 2, we've got 1, and if we add 3 again, we have the identity. So yes, 3 generates Z4. Does 0 generate Z4?
No.
Why not?
It can only be 0.
Exactly. Nope. How about 2? So sort of a more interesting question, right?
Also no, because It can either be 2 or 0.
Plus 2 gives 0. Exactly. So, in fact, 2, generates the subset 0, 2. But the thing it may be worth noting here, is this subset a group? Well, is this a group?
Yes, right? Yeah.
I agree. Why? Check the axioms.
Yeah.
1. So let's see. So is there an identity? Yes, 0. Is it associative? Of course, since addition is. And in particular, its operation is associative because it's a subset of a group which we already know had a valid operation. So we're keeping the operation of the main group. So of course that operation is still going to behave nicely. Inverses, yes, 2 is its own inverse. So 0, 2 is itself a group contained within C4. We call this a subgroup, obviously. I mean, not obviously, but predictably, right? Of course, like this, we're just saying that a subgroup is a subset that behaves like a group. So C4 contains, what's happening with this? Okay. C4 contains the subgroup 0, 2, which behaves like a group itself. This subgroup is generated by 2. So in particular, we call this, well, let's do one more thing. Is C4 a subgroup of itself? What do you guys think?
Yeah, because yeah.
Yes, because yeah.
And my other question. Yeah, so and why is it that why is Z4 a subgroup of itself?
Because it's a group that behaves like a group. I don't know.
It's a group, behaves like a group, it's contained within Z4.
Yeah.
It's not a proper subset, but it is a subset. And then what about just the set 0? Just in this case, just the identity.
Also, yes. Not very interesting, but yes.
These are called the trivial subgroups. Every group has trivial subgroups itself and the identity, and maybe just the identity. Let's do that for some semblance of grammar. So yes, every group has these 2 subgroups, but as we've seen, we also can have other subgroups. We have the subgroup generated by 2, right? And we call these cyclic subgroups. In fact, let's see. Groups can also have other subgroups like the cyclic subgroups, which are generated by taking all powers of some group element. Formally, if we have some element G and G, some little g and big G, generates the cyclic subgroup denoted by just G in parentheses, which looks like this. We have the identity, we have G squared, G to the third, G to the N. Stopping only when, when should we stop?
When things start to repeat, right?
Exactly. G to the N, this should be G to the N plus 1 is already in G. And so are we always guaranteed that this is finite when G is finite? What do you guys think? Could we ever have some finite group where all the powers of some element are, well, first, I mean, this is well defined. I should mention this is well defined because, you know, every time you take another power of the element, that's multiplication of two elements in the group. So under closure, it has to still be in the group. And so we can sort of keep getting new elements that way until we run out of new elements.
So
but
it does guarantee that it's finite though, right? Because it already has to be in the original.
Right, exactly. So yes, because G is finite, yes, because G is finite, you might think of this as like pigeonhole principle. There are only so many elements in G that G to the N could be. Eventually, one of them has to repeat. In particular, we say this is the order of the group G and is how many elements it contains. So G, the cyclic subgroup generated by G has at most the number of elements that G has. This happens only when G generates all of the big group. So here, the cyclic subgroup generated by 1 is the whole thing. The cyclic subgroup generated by 2 is 0, 2. The cyclic subgroup generated by 3 is also the whole thing. And the cyclic subgroup generated by the identity is just the identity, which is the trivial subgroup, a trivial subgroup. So why do we care? Well, this is all well and good, right? We're dealing with integers under addition, mod, whatever. But I've just shown you that every group is equivalent to the group of symmetries on some graph. Or sorry, is equivalent to some collection of symmetries on some graph. So what in the world could Z4 possibly be? well, we could go and construct the Cayley graph, right? That would be fine. We would get some graph, which these are certainly the symmetries of. But we don't need to do that. This group, C4, is rotational symmetries of a square. If we say 1 goes to, let's just go 90 degrees, 2 goes to 180 degrees. Come on. 3, where does 3 go?
270.
Yep. And then obviously 0 degrees. So this is sort of part of the reason that I say we don't need to have all of the symmetries, because this isn't all the symmetries of the square, but it is the rotational symmetries of the square. You may be familiar with this as, you know, the integers mod n, say the integers mod 12, we have a clock, right? And we move around the clock. That's the same as rotating it. So this vertex goes here, and this vertex goes here, and et cetera, right? So when we talk about moving around a clock, we're really talking about the rotational symmetries of a clock, which is Z12. How do we feel about that? Questions?
No, it makes sense to me at least.
Good. All right. That's what I wanted to get through on this first installment. I wanted to talk, let's do our very brief recap. I wanted to talk about the group axioms, the notion of symmetry, and how groups are sort of totally inseparably linked with the idea of symmetry. And then talk about some very basic groups like the Klein 4 group, like Z4, like the group of symmetries of a square, and talk about the notion of subgroups and cyclic subgroups in particular. That concludes what I have to say on this first installment of introductory group theory. Thank you guys for, well, thank you viewers for viewing, if there are any. And thank you guys here in the call with me for asking some good questions and being a good sounding board here for me. All right. Thank you.
Hey, no problemo.